All right, so today what I want you to be able to do is that we're going to talk about something called reference angles, and you'll be able to find reference angles today. And then the other thing that you'll be able to do is that you'll be able to use points on a terminal side to evaluate trig functions. Okay, those are like the two things we're going to do. So let's start by talking about reference angles. So I know yesterday we talked about coterminal angles, which are like those angles that are in the same position where they end, but it'll be like multiple rotations or going the other direction or whatever. So today we have a different kind of angle we're going to talk about, and that's a reference angle. So reference angle is an acute angle that's formed between the terminal side of theta, which is our angle, and the x-axis. So it must be positive. So we have this picture here that's just kind of like a way of telling you how to find your angle. So we're going to draw an angle in standard position. So we have our initial side, our terminal side. Here's our angle. So if you end up in quadrant 2, the way to find what your reference angle is, the reference angle is describing this little bit right here, where it's like from that angle down to your x-axis. So algebraically, you do that by doing 180 minus theta. That's not a 0, that's our theta. If you were in radians, you could do this by doing pi minus theta, right? Because pi is 180 in radians. If you drew your angle and you ended up in quadrant 3, so again, we want this reference angle. And I know we're tempted to say, oh, it's that direction, so it's negative. Reference angles, we don't consider negative or positive. So you would do your angle minus 180 to get that reference angle, or you do angle minus pi. If you drew your angle and you end up in quadrant 4, we're looking for this angle here, you would just do 360 minus theta, or if you were in radians, 2 pi minus theta. So for this part, really, I'm asking you to draw an angle and do some subtraction. So let's look at example 1a. We're going to find the reference angles here. So for 140 degrees, if we were to draw 140 degrees, and again, you can just eyeball it if you want a protractor. You can use one, but it's about like that. So we have this initial side. That's our terminal side. We rotate like that. So then my actual reference angle is this little bit right here. So to find that reference angle, since I ended up in quadrant 2, I would just do 180 minus my given theta, which is 140 degrees. And I end up with a reference angle of 40 degrees. Okay, so our reference angle for 140 degrees would be 40 degrees. Part B, again, same idea, 320 degrees. If you were to draw this out, our initial side is here. I would rotate about to here, all the way around like that. So then my reference angle is going to end up being right here. So this is 320 degrees. I ended up in quadrant 4. So the rule is then that you just take 360 minus my 320. And we end up with actually the same reference angle of 40 degrees. So strangely, we got the same reference angle for a different initial angle. Pretty straightforward so far, right? Yeah. Any questions so far? Okay, let's look at 2 that are a little more complicated, and they're only a little more complicated because one is negative, and actually they're both over 360 degrees. So this negative 515 degrees, if I wanted to find the coterminal side for that so that I can actually draw, I would just add 360 degrees. So I would get that the coterminal angle with negative 515 degrees would be negative 155 degrees, okay? Minus 1 rotation. So that means I would end up here about, and technically I went through, so I started here and I went through twice. So I went once, twice, right? We had 1 full rotation. You guys remember doing that yesterday? So this is technically negative 155 degrees. Not technically, it is. And this is my reference angle here that I want to find. I'm in quadrant 3. So I'm just going to take 180 degrees minus 155 degrees. Now I know it's weird we didn't do minus minus, but you just like stick with the positive version because again we don't want to like worry about different actually technically it would be that theta minus, but whatever. I did it backwards, it's fine. You get 25 degrees. I did do it backwards. It should be theta minus 180, but you can just make it positive and consider it that way instead. Any questions about that one? That one's weirder. Always subtract by 360. Oh, yeah, you'd add the 360 just so that you know where to graph it. So this one, when I went through, I want to find what the coterminal angle is so that I can graph this because I have no idea where 1,234.5 degrees is. So what I did when I was working on this answer key is I just took this number, I did minus 360. Okay, that's one rotation. Minus another 360, that's two rotations, three rotations. Okay, that puts me under 360. So technically what I did here was I just subtracted 3 times 360 to get that my coterminal angle is equal to 154.5 degrees. And if I graph that, that would end up right about here. It's 154.5. So I ended up in the second quadrant, so I'll use this rule where I do 180 minus 154.5, and I end up with a reference angle of 25.5. So as long as your reference angle is positive, it should be under 90 degrees, right? Because it should be if you're subtracting 180 or 360. That's also why there's not a rule for quadrant 1, because technically any angle that's in quadrant 1 is its own reference angle, right? Does that make sense? So that's why there's not a rule for that. How do we feel about reference angles? Good. Good. So your homework does have some that are in radians. So if I give you something in radians, you can convert it to degrees and then get your answer and convert it back. But I want the answer in radians and vice versa. Yeah.
Do you have to draw like the arrows showing that you're going around?
Not multiple times necessarily, but you'll want the arrow just to see what like quadrant you're in.
For D?
For D, I didn't draw it. Yeah, I should technically, I guess, like 3 times, but it just makes the picture messy and it doesn't affect my answer. So it's fine. Yesterday, I wanted the multiple rotations, but today, since we're not talking about coterminal specifically, it's fine just drawing it.
Okay, thank you.
Okay, so the other thing I want you to do is this stuff right here. And I actually want to show you this pretty little picture. Did I exit it? Okay. So this is sort of my intro to a unit circle, which again, we're going to do tomorrow. But I want you to picture that you have some circle on a coordinate plane. And any point on the circle makes this right triangle, right? So this particular circle has a radius of 1. That's not necessarily always the case, but our unit circle is a radius of 1. That's why it's special. It's called the unit circle for that reason. But I like this little app because you can see that any point on this circle makes a right triangle. And anytime you have a right triangle, your trig functions pop out, right? So you can consider, so if you have this triangle here, this is our theta, right? And it happens to be at 45 degrees. That's just lucky. They didn't give it to us as a fraction. They reduced it as a decimal, but that's not important. What we have here is we have that this is a side length. This is a side length. You could use the distance formula or the Pythagorean theorem to find your hypotenuse. And then you can find all your ratios of your trig functions. So that's actually what we're going to do today. And I just want you guys to see that we can make all these different triangles with this circle. Why we do this random unit circle with our trig functions. So if you look above example 2, they give these all so that we have like the formulas for them. But we're actually just going to draw them out so that you can kind of see exactly why it works the way it does. So we do have these, but let's just look at it on a coordinate plane. So example 2, let the following points be points on the terminal side of theta. Evaluate the 6 trig functions of theta. Again, theta is our angle. So we have a point at -4, -3. So let's go ahead and graph that. On my x-axis, I need 1, 2, 3, 4. 1, 2, 3. So I have this point here. So once you have a point, you always draw a diagonal line from the origin, and then draw up or down or whatever way you need to get to the x-axis. And notice we made this nice right triangle. And what I know about this right triangle is I know that this distance here is -4. And this distance here is -3. Now, it's a little weird to have negative side lengths of a triangle, but we are going to do that because it does tell us like what quadrant our triangle is in. So that is important, and it'll pop up in our unit circle as well. So again, I know it's weird to have like a negative distance, but we'll just deal with that today. So what I need to find is this hypotenuse right here. So I can actually use the Pythagorean formula here, and I have hypotenuse is equal to the square root of a leg squared plus a leg squared. So if I just plug these in, and I heard, I think Reva maybe during the booklet say something about I love Pythagorean triples. That's true. If you see it's a Pythagorean triple, four of your 5 homework problems today are Pythagorean triples. If you see one, go for it. There's one that's not. So if you know your Pythagorean triples, that's great. If you don't, you run through this, you'd have the square root of -3 squared plus -4 squared, the square root of 9 plus 16, square root of 25, so you get 5. And again, maybe you recognize this is a Pythagorean triple because I have -3, 4, and 5. Notice the 5 I don't make negative, you just leave it positive. I think the hypotenuse is always positive. Yeah, I'm going to say the hypotenuse is always positive. I don't know why that is, but just bear with me. So once we have all our sides of the triangle, we can go through and we can name. So, and actually, let me be specific here. The theta we're talking about, because I know we have a right triangle here. We do have an angle here, but this is always the theta we're talking about, the one that's like connected right with the origin. Yes, the acute one. It's not necessarily always the acute one, though. It could be the obtuse one sometimes, depending on where you're at. So then my trig functions would be sine of theta, cosine of theta, tangent of theta. And then we talked on whatever we did 9.1 last week. We talked about the other trig functions that like correspond with these, the reciprocal ones. So sine's reciprocal is cosecant of theta. Cosine's reciprocal is secant of theta. And tangent's reciprocal is cotangent of theta. So remember, cosecant is 1 over sine, right? It's like the flip of it. So that makes this pretty easy for us because then we're just going to fill in our trig functions. So sine relative to theta would be opposite over hypotenuse. So it's -3 over 5. And this is really nice because then I already have my cosecant would be -5 over 3. So you can see if I don't give you a Pythagorean triple and you have a square root floating around, you do have to simplify. You do have to rationalize all that stuff. So one of your homework problems does that. Cosine of theta relative to this would be adjacent over hypotenuse. So -4 over 5. And then secant would be -5 over 4. And then tangent would be opposite over adjacent. They're both negative. So it would end up simplifying to 3 over 4, just positive. And your cotangent would be +4 over 3. So on Go Formative, you have 5 of these questions where it's a fill in the blank. So for the one, you will have to copy and paste the square root. Sorry, it's not beautiful. Someday Go Formative will do those for me. Do we feel pretty decent about this? Wait, do you guys want me to do example B where we have a square root? Okay, so you have one problem on your homework that does the square root. The rest, I think, are Pythagorean triples, if I remember right.